Alright, this is part 2 of things rolling down ramps. Before we can do something rolling down a ramp, we just need to look at what it looks like when a thing rolls flat on the ground. So let's say there's a wheel rolling along the ground. So it's got some angular velocity, and the center of mass has a velocity which we will call u. If the center of mass has that velocity, then the overall object is making that progress along the ground. So if u were 10 meters per second and this wheel rolled for 1 second, it would have moved 10 meters. So center of mass velocity tracks the object as a whole, and that's basically the velocity we've always been talking about. We just never called it center of mass. But now, since objects can rotate, each point on them doesn't necessarily have the same velocity. Before we started talking about rotational motion, anytime an object was moving, every point on that object had the same velocity, so we didn't need the concept of center of mass velocity. But now, since the point at the top and the point near the bottom and this point are all going to have different velocities, you still need some way of referring to the overall velocity of the object, and that's center of mass velocity. It is technically the velocity of the point, which is the center of mass of the object, if that's not clear. So I drew these few dots for a reason, because that's typically the points you look at when you go to describe the different velocities of points on an object that's rolling. So the center of mass does not have any velocity associated with rotation, because it's not rotating. Well, I mean, technically it might be rotating in place, but it's not actually moving around in a circle like all the other points on the object are. So it's the simplest point to draw a velocity for. The other points will have two velocities, and I think I mentioned this in the last video, but the two velocities are the translational velocity associated with the whole object moving across the ground, and the rotational velocity associated with each point rotating around the center of mass. So if we draw the rotational velocities, I'm going to draw them all in red. So let's say the rotational velocity of this point on the top is to the right. In the last video I called this tangential velocity, because if you draw a line to the center of mass, this velocity is tangential to that line. But that rotational velocity actually is different depending on how far away the point on the object is from the center of mass, or from the axis of rotation. In this case, the axis of rotation is the same thing as the center of mass. Because remember the formula we looked at in the last video, v equals r omega. This is really tangential velocity, and this r is really just however far away you are from the axis of rotation. Omega for us stays the same. Well, for now, it stays the same. We will look at some situations where omega could change if the object had an angular acceleration. But so this point's tangential velocity around the center of mass is not going to be as large as the point at the top, because the point at the top is farther away from the axis of rotation. So if this point is literally 1/2 of the way to the outside edge, then because it depends on r, the tangential velocity would also be 1/2. Down here, this point has a rotational velocity backwards, or a tangential velocity backwards, because the lower part of this wheel is actually rotating this way, the upper part is rotating this way. So this is why you need the concept of center of mass velocity, because the velocities of all the points get rather confusing when you start looking at all the possibilities. And this bottom point would have a velocity comparable to the top point, but pointing in the other direction. And so these are larger the farther away you are from the axis of rotation. But each of these points, so those are the velocities associated with rotation. Each of those points also has a velocity just like the center of mass does. So if we draw that vector on there, that's a green vector that should be identical to the one I drew in the middle. I might struggle to draw them identically, but every one of these points should have that same vector that exists in there, and those are all u. They should literally be the same length and the same size as the center of mass velocity. So each point has two different velocities associated with it, but when you add those two vectors together, you get the net velocity of that point. And so if we do that, the result will look something like this over here. So the center would still just have center of mass velocity. The top would be center of mass velocity plus a rotational velocity. I'm going to draw all of these green ones before I change colors. Oh, I forgot what I was doing. Let's just draw the net. So the top would be actually longer. It would be u plus r omega, if this distance is r. This one would be larger than the center of mass velocity, but not as large as the one on the top. So u plus 1/2 r omega, if this is actually half the distance to the outside edge. That's what this one would be. This one would be actually u minus 1/2 r omega, and this last one would be u minus r omega. And so this bottom point is of note. If u is r omega, or if r omega is the same size as u, then the bottom point or the point of contact with the ground, does not, I'm running out of room here, slip. And so slipping is previously what we called sliding. You know, if you let a block slide down a ramp, then there's friction because there's sliding motion. And so if an object is rolling and the center of mass velocity u is the same size as the radius of that object times the angular velocity, then that bottom point will have a total velocity of 0. If those things are the same size, then this would be 0, and therefore that bottom point technically has no velocity, which sounds really weird, because obviously this object is moving forwards along the ground. But you think about this as one instant in time. That point on the object just simply doesn't have a velocity because its two vectors are pointing in different directions and they cancel each other out. Now, if you let time move forward one instant, then obviously that point is then farther up, and now it does have a velocity. And the point that doesn't have a velocity was previously over here and it moved. So like the point of contact is constantly changing. Which point on the tire or wheel or whatever this is in contact with the ground, that point is changing. But in each instant, that point has no velocity. So understanding that about the point of contact not having a velocity is a pretty big deal in understanding rolling motion without slipping or sliding, because it's pretty it's more complicated to explain rolling motion if that point can slip and slide. That's not to say that you can't explain it with physics. That would be like a car hitting the accelerator so fast that the tires start spinning out, or when you go to stop and your tires start to slide, but they're still spinning as well. Those situations would not be explained by the physics we're going to do with rolling objects, because all of the rolling motion that we will study will be rolling without slipping. Okay, with that understanding under our belt, we can begin to think about what's going on when an object rolls down an incline. So let's say we have a cylinder on an incline like this. And I said it was a cylinder, so we're going to need the moment of inertia, or the rotational inertia of a cylinder. So in IB physics, that means it has to be supplied to you, because we aren't going to be ever finding these formulas. So here's a solid cylinder or disk rolling or rotating around the axis of symmetry. That's exactly what we need. So the moment of inertia for that object is 1/2 times its mass times its radius squared. So that's what we need. 1/2 times mass times radius squared. So yeah, let's say this object's mass is m and its radius is r. And we want to know, how does this object's acceleration compare, if it's going to roll down the incline, how does the acceleration of that compare to if it were just a box that slid down the incline? And to remind you, sliding down the incline would result in an acceleration of A equals g sine theta. If there was no friction and a thing just slid straight down the incline, we would get that result. And if you don't believe me, you have the tools to prove it to yourself. But this thing is not going to slide down. We're going to let it roll down, rolling without slipping down this incline. So we need to use, if you were going to go derive this formula, you would look at the forces on the object and you would write down Newton's second law and you would plug in the different forces and you would solve for the acceleration. Well, that's exactly the recipe we're going to follow, except we need to look at the forces and then think about what torques they cause on the object. So if it is going to roll without slipping, that's actually impossible in this situation unless there is friction. Because if there were no friction, the forces on this object would just be gravity and the normal force. And the normal force acts at this point upwards, and if you extend that line of action of that normal force or reaction force, I shouldn't call it R because that's the radius. I'll call it FR, reaction force. That goes through the axis of rotation. So this normal force or reaction force will not exert a torque. And if we draw gravity on here, that's the weight. The weight also acts through the axis of rotation. So the weight also does not exert a torque. And therefore, if neither of these forces exert a torque around the axis of rotation, then the thing's not going to rotate. So you have to have friction in order for a thing to begin rolling. More technically, you have to have friction if you want an object to be able to accelerate, to have an angular acceleration. Because otherwise, there's nothing providing a torque. And so if friction exists, then it would be a force that acted on this cylinder at that point of contact and back up along the ramp. Because remember, to figure out the direction of friction, it just opposes motion. So if this thing were going to slide down the ramp, in that direction, then friction would resist that slide. And the only place where friction can exert a force on this object is that point of contact. So this would be the force of friction. And if it's rolling without slipping, that is technically static friction. Because remember, the velocity of that point of contact is 0 if this is rolling without slipping. That surprises students generally, because they see an object moving, they think kinetic friction, dynamic friction. But that point of contact actually is not sliding or moving. In each instant, the point of contact has no velocity, therefore it's static friction that is the force in rolling motion when there's no slipping. So here are the forces on the object. Now we need to calculate the torques that each of them exert around the axis of rotation, which we'll say is the middle. Well, we already said that reaction force and weight don't cause a torque, so the only force that does cause a torque is static friction. So sum of the torques around, let's say that's the center, point C. Sum of the torques around the center equals I times alpha. But I know it's rolling down the ramp, and it's going to, in the drawing that I made, it's going to roll clockwise, so let's just say positive is clockwise. Static friction would exert a force that would rotate it clockwise, so that would be positive torque. So the force is Fs, the distance from the axis of rotation. So remember, when you calculate torque, you need the distance from the axis of rotation and you need the force. And I'm using the method where here's the line of action of friction. The shortest distance to the axis of rotation is just the radius. So I can multiply that distance by the force. So that torque will be causing I times alpha. I is 1/2 times m r squared r fs. So already one of these r's cancels out if I divide it. And we've got this fact. Static friction is 1/2 m r times alpha. All right. That doesn't tell us the linear acceleration of the center of mass of the object, which is what I'm trying to solve for. That's an expression that involves friction and angular acceleration. So I need to look at the sum of the forces in the x equals mass times acceleration in the x, and I need to look at the sum of the forces in the y. That's going to be mass times acceleration in the y. Now, when you use, so this was rotational. When you use the linear versions of Newton's second law, or the older versions, the acceleration that you get is technically the acceleration of the center of mass in the x direction. The acceleration of the center of mass in the y direction. So they still work, it's just that you need to know those accelerations you're solving for are of the center of mass. So we can still use these equations. Let's say that down the ramp is positive x and perpendicular to the ramp is positive y. So that means negative fs plus ramp physics. If this is theta, then this angle is also theta. Prove that to yourself if you forgot. And so w sine theta would be this component of the weight, which is along the ramp. That's the x component of the weight. So plus w sine theta equals m a center of mass in the x. In the y, we could go ahead and do it. I don't know if we'll need it. In the y, we have reaction force minus w cosine theta equals m a center of mass in the y, but we know that's 0 because the center of mass is going to move along this line, and it's always going to be r away from the ramp, so it does not have a y acceleration here. So if we need reaction force at some point, it's w cosine theta, which is similar to old ramp problems. All right, now we need to relate. So we have angular acceleration, we have linear acceleration. Well, just like on the last page I said the velocity of the center of mass has to be equal to r times omega if it's rolling without slipping. There's another relation that is a direct result of this one, that is the angular acceleration, the acceleration of the center of mass has to be r times alpha. And the easiest way to show that this is true is to just take the time derivative of both sides of this equation. So the derivative with respect to time of velocity, the definition of that is acceleration. And r doesn't change with time. So the derivative of angular velocity with respect to time is just angular acceleration. IB's never going to ask you to prove this, so the fact that I did it with calculus is okay. There are other roundabout ways you could prove this has to be true if a thing is rolling without slipping and also it's accelerating. So this relation can allow us to link these two equations together. And the only tricky part about this is you have to pay attention to directions. Because I chose x down the ramp as positive, and because I chose clockwise as positive, and because this object is doing those things, I'm not going to fall into any traps. But depending on how you pick your axes, like if I had picked x up the ramp is a positive acceleration, then this equation would not technically be true, because an acceleration up the ramp would not equal an angular acceleration clockwise. And so in that situation, I'd have to plug in my own negative sign to make sure that the relation was true. But however, that's not a problem here, because down the ramp and clockwise are positive, and that's what the object is actually doing. So a center of mass will equal r alpha. I don't have to throw in a negative sign. So I'm trying to solve for acceleration of center of mass. So I want to substitute, I'm going to say alpha equals a center of mass over r, and plug that in over here. So friction equals 1/2 mr times a center of mass, and technically this is the x direction. That r cancels, and I'm left with this. This says friction is 1/2 times m times a center of mass in the x direction. Well, I can plug that in here for friction. So actually I never even needed reaction force to solve for what the friction is, because so that would be negative 1/2 m a center of mass in the x plus w sine theta equals m a center of mass in the x, and then that's mg sine theta equals m a center of mass in the x minus 1/2 m a center of mass in the x. M's cancel from everything. This becomes 3/2 a center of mass in the x equals g sine theta, and so a center of mass in the x becomes 2/3 g sine theta, which is smaller than g sine theta of a thing just sliding down a ramp. And the only thing that's different if this shape is different is you just plug in a different moment of inertia.